looking at the binary coding. We did the binary coding yesterday, and I'm going to go over one more example so that you can have a clear understanding. So I'm going to find binary coding of 37. I'm going to use my writing board so that you can see how it goes. To find a binary code of 37, basically I have to express 37 as sum of powers of 2. So I write 37 and then equal to then I had to write sum of powers of 2. So you start at 2 to the 0 at the end, and 2 to the 1, 2 to the 2. Now you have to decide what is the largest power we can have. So
2 to the 5.
2 to the 5, right.
Yeah.
2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. And we cannot have 2 to the 6. So I stop there. Okay, so now I have to decide whether to put 1 or 0. Now the largest power will always have 1. So you start by putting a 1. You know, we need to include that number right there, 32. And then these things have to add up to 37. So what are the other numbers we need? If I put plus 0, if I put 1 in front of 2 to the 4, that will add 16 to this, which is too much. 16 plus 32 is too much. So therefore, that'll be 0. And then plus, if I include this, 2 to the 3, that'll be 8. 32 plus 8 will be 40. So that's also too much. So 0 there. And 2 to the 2 is 4. I can include that. So therefore, I put 1 there in front of that. And plus, so that's 1 means 4 included. 32 plus 4 is 36. So I cannot have another 2. So 0 times that. I need a 1. So I need 1 times 2 to the 0. Okay, so 1 second. Okay, so 32 plus 4 plus this equal to 1. So that is equal to 37. So therefore, these digits that are in front of powers of 2, these will make up the code. 1, 0, 1. So that'll be 1, 0, 0, 1, 0, 1. That is our binary code for 37. So I hope you tried 78 and 65. So anybody can tell me the code for 78? You're supposed to do it at home.
Yes. Give me a second.
Okay. Nobody has it?
It's 1001110.
Okay, 1001110. Others have the same thing? Anybody
Yes.
else?
I agree.
Okay. All right. So that sounds right. Even number has a 0 at the end. Sounds right. So I'm going to move on because I have already explained how to do this. So, you know, you were supposed to try this at home. So I hope all of you tried it. Otherwise, if you're going to have to try it yourself. And if anybody needs my explanation on those two questions here, 78 and 65, I will explain that. Now, by the way, I have office hours at 2 o'clock Mondays and Wednesdays, and your tutor will meet with you at 4 o'clock on Thursdays. The tutor will do the same. He will wait for 10-15 minutes, and if nobody shows up, then he will leave. And same thing I will be doing. So if you need help, you had to be there. You had to be there at that time, at the beginning time, which is 2 o'clock for me and 4 o'clock for the tutor. So let me move on and explain to you how to go backwards. If I give you a number, binary number 100101 and ask you to find the decimal equivalent, how do we do it? Well, basically we have to write this last one, start at the last one, and that corresponds to 1 times 2 to the 0. Clearly, you know, this last one is supposed to be the coefficient of 2 to the 0. And then I have 0 times 2 to the 1, 2 to the power 1, plus that, plus 1 times 2 to the 2. You have to count from the bottom. 2 to the 0 for the last one, 2 to the 1, 2 to the 2. So 1 times 2 to the 2, plus 0 times 2 to the 3, 0 times 2 to the 4, 1 times 2 to the 5, 1 times 2 to the 5. I didn't write the zeros because they'll add up to 0. So 2 to the 5, now we had to evaluate the whole expression. 2 to the 5 is 32. So write 32 plus 2 to the 2 is 4 plus that's 1 times 2 to the 1. Yeah. So that's 2 plus 1 times, no, this is 0, sorry. Yeah, this is 0, so that doesn't, no, 2. 1 times 2 to the 0 is just 1. So 32 plus 4 plus 1 is 37. So that's how you go backwards from the binary code. You had to start at the bottom. Last digit corresponds to 2 to the 0. Next one corresponds to 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. You write that expression and simplify it. Okay, so that's 37. Now, I'm not doing any example on this, but you will be doing problems in the homework. So if you're not understanding anything, please feel free to ask the question. I will explain again. There is a shorter way to find binary code. Now, I wanted you to do it the longer way first, because that gives you the understanding of what binary code is. Now I'm going to explain the shorter way, because you will be finding binary codes in your homework very often, and therefore I'm going to tell you the quicker way. Okay, so here is a quicker way to find binary code. I'm going to explain on the board. What you do is you divide that number, given number, in this case 37, by 2. 2 is our base, so you have to divide it by 2. 2 goes into 37 18 times with the remainder of 1. The remainder will be either 1 or 0. You write that on the side. Divide by 2 again. 2 goes into 18 9 times with the remainder of 0. No remainder means write a 0. Divide by 2 again. 8, 2 times 4 is 8, so remainder is 1. 2 goes into 4 2 times, no remainder. You have to keep doing it until you get number less than 2, which is 1. So 2 divides the 2 into 1 time with the remainder of 0. This last remainder is the one often missed by the students. You must write every remainder. Now, if you read the remainders from bottom up, that'll be your binary code. Bottom up means this one, the one will be the first. 1 0 0 101. If you remember, we did find the binary code of 37 earlier, and that was same as this. So, you know, basically that's what you need to do, right? Divide by 2 repeatedly and write down the remainder on the side. So I want you to find the binary code of 86 right now using this short method. 86. You can use calculator if you're not good with the mental division. Um, Anybody has the code?
1010110.
Okay,
Yes, same.
same thing. All right.
I agree.
Another one. Okay, very good. Let me finish myself anyway. 2 goes into 5 2 times. 1 remainder. 2 goes into 2 1 time with 0 remainder. So 1010110 is correct. Very good. That is correct code. So I'm going to move on. I have to think that you got it. Okay, so ASCII code. Now we discussed ASCII code before. One more time. Every character and every symbol, even the symbols we use, like mathematical symbols like alpha, beta, you know, you're not familiar with that. Plus and minus, these are all coded in this language. So every symbol out there and every alphabet in English has a code. And each one of those code has 8 bits, 8 zeros and ones. So always characters have 8-bit code, but the numbers, depending on the size of the number, it may be more than 8-bit. So we'll be discussing numbers a little bit more later in the next section, but right now we'll understand the ASCII codes for the characters. So all these ASCII codes, codes for the characters that were designed by the very first company that built the computer. IBM was the very first company that built the computer, and they designed this language, and they named it as American Standard Code for Information Interchange. So the first letters of those words make up this word ASCII, ASCII. So real name is American Standard Code for Information Interchange. So the name of the language became ASCII or machine language, but generally used name is machine language. So if I ask you a question, what is the language of the computer? Your answer would be machine language. If you say ASCII, that's not incorrect, but more common name is machine language. Okay. All right. Moving on. Yeah. So ASCII code of letter A is this 01001, and one of my exercise for you to do before this class was finding binary code of 65. And if you found it, you may have found that binary code is equal to this, 010001. So what does that mean? The ASCII code of A and the binary code of 65 are same. Now, by the way, ASCII code of the numbers would be same as binary code of the numbers. Only the ASCII code of the characters were just designed by the IBM, and we have to just use that. So the ASCII code of A happened to be same as the binary code of 65. So therefore, when the character A is stored in the computer memory, this code will be stored. When the character 65 is stored in the memory, the same code is going to be stored. So how does the computer know whether you have stored a character or a number, whether you have stored the character A or the number 65? How does it know? Anybody? Well, it doesn't.
You have to tell it.
You don't even have to tell it. Computer doesn't need to know anything. Basically, you store the A065, it'll have these bits in there. And does it know whether it's a character or a number? No, it doesn't. And no, it's a programmer who knows what he's told, what he or she is told. And then if you want to get it out in the same format, you can get it out. If you want to get it out, convert it to the opposite format, like you store the 65, then this will be stored, this binary code will be stored. And then if you want to get it out as a character A, you can do that too. So it's all programmer who manipulates how to work with that and what to get out. Or even so, if you do arithmetic with these characters, computer will do it because it doesn't know whether you're doing arithmetic with the characters or numbers. It'll do it. So if you add A and B, you'll be adding 65 and 66. The code of B is same as the code of 66. So if you add the characters A and B, you'll be adding 65 and 66, and the computer will do the arithmetic for you. So basically, it's the programmer who decides what you want to do with it and what you don't want to do with it. So basically, in the computer doesn't really understand what you're storing. The programmer, has to keep track of it. Let me show you now some of this ASCII codes. The characters A through Z, uppercase A through Z, have codes that are equivalent to 65 to 97. So 65 to 97 are called the decimal codes of the characters A through Z. The lowercase, I'm sorry, 65 to 90, sorry about that. 65 to 90 will correspond to A through Z uppercase, and lowercase a corresponds to 97. So what do we have between 90 and 97? Some other symbols. Remember, all those symbols are also coded using binary ASCII codes. So the symbols, mathematical symbols, and even decimal point, and all those have codes. So some other characters are there between 90 and 97. We don't have to worry about it, but it'll be helpful to remember these ranges. But if you don't, even if you don't remember, you need to use them in your some of the questions, and therefore it'll be provided in your tests. The range, uppercase letter A through Z correspond to 65 to 90, and lowercase a through lowercase z correspond to 97 to 122. This information is often necessary to answer the test questions, and I will provide them in the test. You don't have to memorize them, but it helps to know. I mean, eventually, after you do several problems, you will remember. But anyway, that range would be necessary to answer some of the questions. So let's go into, for example, if you want to write a code in your program that will convert lowercase to uppercase, then you basically have to add a number to change the 97 subtract a number to change the 97 to 65, things like that you'll be doing. So let's go to the next page. The character, representing a character in the computer memory. How exactly do we represent a character in the memory? Remember I said earlier, all the characters, to store anything in the computer memory, you had to have a corresponding code, ASCII code that is, which has only ones and zeros. So that's because only ones and zeros can be handled by the computer. Now let's understand now why only ones and zeros can be understood, and how we represent everything using ones and zeros inside the computer. Now the computer is a machine. So when there is power going through it, any machine recognizes power. It comes on, and it recognizes the power. It turns on, and then it'll be able to do things for you, like if it's VCR or DVD player. When you power it on, it recognizes the power. So the machines can only recognize the power, the electricity. They cannot recognize anything else. So that means the machines are recognizing something, right? So that's when the scientists decided that if we can represent everything using power on, power off, two things, on and off, then we can represent everything inside the machine and make the machine recognize that. And that's where the idea of a computer originated. The idea of representing everything inside a machine by using power on and off. On and off are recognized by machines. So what they had decided to do was arrange a whole bunch of circuits and turn them on and off in a pattern. Then the machine can see the pattern of the circuits having power and not power. So some circuits have power, some circuits don't have power. The machine can recognize which circuits can have the power. And so that means if we can represent everything in our world using two things, then we can represent everything inside the machine. That's where the idea of computer originated, and that's exactly what we are doing in the memory of the computer. We are turning circuits on and off in a pattern to make the system recognize our characters. So for example, for everything, we'll be turning circuits on and off. So a whole bunch of circuits are inside the memory now. Each circuit is going to be turned either on or off. So when a circuit is on, that means there is electricity going through it. And when the circuit is off, there is no electricity. So we will represent, in our pictures, we will use this closed circuit to mean like this one on the left to show a circuit that is on. An open circuit like this will be the circuit that's turned off. So using that, we can show on a picture exactly what the memory will look like after storing a character. So the memory means the RAM, the computer memory. Inside the memory, which is RAM, 8 circuits will be selected. Anytime you store a character, 8 circuits will be selected to represent that character. And those circuits will be turned on and off according to the pattern of the ASCII code that we have for that character. So to represent 1, a circuit will be turned on. To represent 0, a circuit will be turned off. So in our ASCII code, we write 1 and 0, but really inside the computer memory, they will be on and off. So remember, 1 will be on, 0 will be off. You have to use that coding correctly. Okay, so there is here is a memory setting of the letter B. The letter B has the ASCII code equal to this. So if I store the character B in some way in the memory, you will be learning later how to write a statement in the program that'll tell the computer to store the character B in the memory. So if I store a character B, then immediately a set of 8 circuits will be selected and they will be turned on and off according to this. Now this picture may be confusing. I should have, I recommend actually, in fact, when you do your homework problem, use separate circuits like I'm doing on the board now. Let me see. So the first circuit is going to be turned off. So turning off would be, you draw that this way. And then next one will be on, closed circuit. Next one will be off. So you show that this way. Next one will be off. Uh, 4 offs. 4 off and then on. On will be closed circuit. Off will be open circuit. At least one question in your homework asks you to show the memory setting. So this is the memory setting of 1 byte of memory. This is exactly what we call 1 byte of memory. The memory needed to store 1 character, which is equal to 8 circuits. That is 1 byte of memory set to on and off according to this. So this is what happens when we store the character B in the memory in any way. That means, you may be writing a program that tells the system to store the character B, or you may have started a word processor and started typing your document by punching keys on the keyboard. When you punch the keys on the keyboard, what is going through the wire to the computer? Nothing is going through the wire. The job of the key B on the keyboard is to set the memory is to set the memory this way. Exactly, 1 byte of memory will be set on and off according to this picture by the key B. So every key in the keyboard is designed to set ASCII codes in the memory according to those keys. That's what their job. All right, moving on. This memory used for storing 1 character is called 1 byte. And so 1 byte is same as 8 circuits. The 8 circuits will be called 8 bits because the circuits are going to be used to store the ones and zeros. The ones and zeros are called bits. So therefore, it is accurate to say 1 byte is same as 8 bits. And physically, what is there in the computer memory of 1 byte? 8 circuits are there. So if the question says, what exactly is physically present in the computer memory, your answer would be a whole bunch of circuits. That's all there is. The memory has these small, tiny loops, infinitely many loops, circuit loops are there. And they're buried in a silicon chip because silicon is a material that doesn't conduct electricity. If the material conducts electricity, then the whole thing becomes one piece. So they bury these little circuits inside the silicon chip, and that's what we call memory chip. The material is silicon, and then these tiny circuits are there. If you just open up a memory, you won't be able to see anything because those memory loops are tiny, not visible. That's how they brought the computer down to small by making these loops very small. The very first computer they built it was built by IBM company. In fact, it was 2 faculty members in the math department of University of Pennsylvania. They are the ones who built the very first computer. They had of course, a lot of people did the research leading up to that point. But the people who actually ended up building the computer were 2 faculty members in the math department of University of Pennsylvania. Right here in Pennsylvania, they built the very first computer. And that, how big it was? It was as big as 2 classrooms. That's how big it was. And one of the classrooms was the memory. the memory had to be made by making physical wire loops, loops with electric wires. And imagine 8 circuits are necessary for each letter. So if you want to be able to type up a page-long document, then you need a whole bunch of circuits, right? So that's why the memory has to be very big. And so they made a memory that occupied the entire classroom, and then the rest of it will be in another classroom. So the computer was so big that you have to walk through it to work with it. That's how big the computer was. And then the two professors who built the computer decided that, even though this is huge, it still has a lot of value for businesses. And at the time they only thought about the businesses. So they decided that it has a lot of value, and they actually quit the job. Who wants to be a college professor when you have something big in your hand? So they started this company called IBM and built machines, computers for businesses. And so they had to be given credit for a lot of the things that have to do with computers. One of them is the ASCII language. They designed the language, and then they designed compilers and things like that. They will be learning all those a little bit later. And so they had to do all the work to create this machine and make it work. And then they were in business for a long time, and then there were other companies started, and slowly other other companies basically built better computers and things like that. And eventually, Apple came along and they built computers that are smaller. They came up with the very first desktop computer, the Apple company. So all these other companies finally took over, and IBM is no longer in computer business, and they're gone. So anyway, you must give them credit for a lot of things they did that led up to what we have on our desktop. So let's understand a little bit more about these characters, how they work. So when we actually type a document using a word processor, every character we type occupies 1 byte of memory. As soon as you press a key on the keyboard, you are using up 1 byte of memory that gets set up to on and off according to the ASCII code of that character. And then when you press the next key, another 8 bits will be set to on and off according to the ASCII code of that character, and so on. So as you press keys, you are setting these memories on and off. So every character you type takes up 1 byte of memory, which is 8 circuits long. So if I type the word math on the keyboard, how many bytes of memory have I used up? How many bytes?
32. 1, 2, 3, 4. I say 4 bytes.
4 bytes.
Right?
32 circuits.
Yeah.
But the byte would be just 4.
Yeah.
Every character takes up 1 byte of memory.
Mm-hmm.
So math has 4 letters, so it'll take up 4 bytes. If I ask you how many circuits are used up, then it'll be 32. Right? So my question is bytes. My question will be most of the time about bytes, but I can ask you a question like, what is physically present inside a computer memory? Then your answer would be infinitely many circuits. It's not infinitely many, it's large number of circuits. That's what physically present. Okay, moving on. So now you can understand why RAM is erased when the computer is turned off. When the computer is turned off, all the circuits are off. There is nothing represented inside the memory, right? The memory in the memory, characters are represented by turning circuits on and off. So you had to have the power. You had to have electricity going through those on circuits that are turned on. Only then the system can recognize the characters. So when the computer is off, all the circuits are off, so there is no more data inside it. So that's why every time you turn the computer on, it has to do the work of copying the entire operating system into the memory all over again. It has to do that all over again because it needs power to hold those in the memory. So when you shut down, you're losing everything. And this is why if you're typing a term paper in the middle of typing it, power went off, now your document is gone, right? That's because the document is held in the memory by power. So if the power is off, everything you typed is gone. But the modern word processors have a way of backing up. So therefore, you're safe in the modern word processors. But, when I was an undergraduate student, yes, I had lost work many times due to power loss on the computer. So it happens. Now, CDs and hard disks. Now, so these, the computer memory is power memory. Everything is held by using electricity. So what about permanent storage? Like hard disk. Hard disk is a permanent storage. It doesn't need power to hold data. Even when it is turned off, the data is still there. Same thing with the CDs and other devices. So how do they hold the data? They use completely different technology. So hard disk works exactly the same way diskettes work. Diskettes were older devices, now not used anymore. But how exactly diskettes work or hard disks? On the surface of the they use this exact same technology the music record players used. The surface is coated with hard coating, which basically is tiny magnets. Tiny magnets are all over that surface. And then when you're recording something, those magnets are turned in certain direction. A certain direction will represent on or one, and opposite direction, magnets turned opposite way will be off. So the magnets are turned in two different directions. Magnets have this north pole, south pole, so you can recognize which way magnet is pointing, and that by having two different directions for the magnets, the 0 and 1 are represented. So to represent 0 and 1, magnets are turned to two different directions. That's how the technology on the diskette or hard disk works. What about the CD? CD, even though it sounds fancy, but this technology is very simple. What you do is to represent one, you punch a hole on the plastic. It's a plastic disc. You punch a hole that represents 1. No hole represents 0. So 1 and 0 are represented by hole, no hole. So when you're storing something on the CD, you're actually punching holes, a whole bunch of holes. So that's why we say burn. You're burning the disk. You are physically burning holes everywhere.
Gotcha. I see now.
All right. So the a hole will represent 1, no hole represents 0. So by arranging the hole, no hole sequence, you are storing character.
Okay.
To punch a hole, you're using the laser technology. Laser is very high concentrated light. That's what laser is. And high concentrated light can be used to burn plastic. That's a very simple idea. So since the laser is used, even to read, you're using a laser head. So you don't need to touch the surface. You can just read the holes and no holes arrangements just by scanning over the surface or scanning using a laser light. So you're reading by using laser light, and that's why nothing is touching the disk, and that's why the disk doesn't get damaged by using it. So the biggest problem with the diskette and the hard disk is over time they get damaged because there are moving things, and there are things that are touching each other, things that are touching the surface of the disk. So eventually they damage the disk. But on the CD, nothing is touching it, so that it lasts longer. It lasts forever, actually. So that's why CD technology is preferred. Nothing is touching the surface, so data will be permanently stored. A CD cannot be reused for the same reason. You know, once you punch the holes, you know, you cannot remove those holes. So that's why you cannot reuse it. All right, moving on. Larger measures are needed to measure the memory because memory is very large. You cannot use bytes to measure the memory. Then it's like using inches to measure the distances between cities. So we have to come up with larger storage measures. So that's what these kilobytes and megabytes are. So let's understand them. The 1 kilobyte is equal to 1,000 bytes. The accurate number is 1,024. Everything is power of 2, actually. But since it's almost equal to 1,000, we just use that 1,000. It's easier to work with the 1,000. You don't have to use 1,024. So a kilobyte is 1,000 bytes. A megabyte is 1,000 kilobytes. So a megabyte is 1,000 kilobyte means, let me write on the board, 1 megabyte is equal to 1,000 kilobyte. Kilobyte is written as KB. And every kilobyte is equal to 1,000 bytes. So therefore, 1,000 times 1,000 bytes, which is equal to 1 million. So a megabyte equal to 1 million bytes. That means how many characters can be stored in 1 megabyte of memory? Remember, every byte is good for storing 1 character. And 1 megabyte has 1 billion bytes. Every byte is good for 1 character. So how many characters can be stored in 1 megabyte? It's nothing tricky.
1 million.
Yeah.
1 million, yeah.
1 million characters, that's right. 1 million characters can be stored. Now, a gigabyte is equal to 1,000 megabytes. And now there's the need for terabytes. Things are getting bigger and bigger. So now we use terabytes. A terabyte is 1,000 gigabytes. So they're all 1,000. So it's easy to remember. The actual numbers are 1,024. But like I said, don't use 1,024. It's common to use 1,000 as the number because it's reasonable approximation. Okay, so my warm-up exercise question here is, well, how many characters can be stored in 1 megabyte memory? You already answered it. If a storage media has 1.2 megabyte of memory available, then how many characters can be stored in it? Anybody?
1,200,000.
1,200,000. That's exactly how you should answer. If you answer 1.2 million, that's not acceptable. Okay, you have to give me a full number, a whole number, because we're talking about characters. So we need a whole number answer. So 1,200,000 is the correct answer for this warm-up exercise 2. Okay, so that finishes section 1.2. I mean, not all of it, half of it. And so your homework questions are 1 through 14, but we're going to do part of the second part of 1. We're going to proceed with 1.2 now. So I'll tell you, I will be probably adding problem 16 to this. So 1 through 14, 1 through 16 will be the exact homework. So let me explain something. In your homework, the book is very carefully designed to have the odd-numbered problems and even-numbered problems use similar ideas. So, and the odd-numbered problems have the answers in the back of the book. So anytime when you do an even-numbered problem, only even-numbered problems will be homework problems, but because odd numbers have the answers. If you do, let's say you're doing number 14 and you're having trouble, I would advise you to look at the previous problem, number 13, the odd numbered problem, and read the solution of it. If you still cannot do it, then read the solution of 13. That'll give you idea to do the number 14. The even numbers problems and odd numbered problems use similar ideas. So therefore, always odd numbered problems will help you with the even numbered problems if you have trouble with any of them when you're doing homework. That applies to entire course. Throughout the course, all of the problems are designed that way. All right, so I'm going to close this. Unless you have any question, everybody's clear?
Yes.
All right, then I'm going to close this one and go on to the lecture 3, which is continuation of the same section 1.2. So let's, the same idea, data representation in the computer. The numeric data, like I said earlier, all the alphabets and other symbols in English language are coded using 8 bits, and that means all those characters can be stored in 1 byte. Each character will take 1 byte of memory. But when it comes to numbers, the code, the binary code of the number is the ASCII code of the number. So depending on the size of the number, the ASCII code may be longer than 8. So we allow longer than 8 bits, which means we have to allow more than 1 byte of memory to store numbers. So depending on the size of the number, you may be taking up 1 byte, 2 byte, or 3, 4 bytes. The language C++ is designed to only allow either 1 byte or 2 byte or 4 bytes or 8 bytes. That's how it goes for numbers. So how exactly do we choose the amount of bytes we need? So that's why we need to have a little bit of idea about binary codes so that we can figure out how many bytes are needed for our number. So we need to go further and understand a little bit more about these storage method for the numbers. So if you store a number that has more than 8 bits in it, then you can only use another whole byte. So you have to use 16 bits. There are no portions of the bytes available. So if 1 byte is not enough for your number, you have to use 2 bytes. So we're going to see how exactly a number that takes up more than 1 byte will be stored. That's our next thing. So let's look at a number 1279. You learned how to find the binary code. So I found the binary code as this for 1279. And that has 11 bits. So when I store this in the memory, I have to use 2 bytes. So if I use 2 bytes, the second half, the 8 ones and zeros at the end, will be stored in the second byte. So this part, is that 8? 3, 6, 7, that's 8, okay. So these will be stored in the latter byte, and these padded with additional zeros in the front will be stored in the first byte. So you only add zeros to the front, because adding zeros to the front doesn't change the value of the number. But if you add zeros to the back, that will change the value of the number.
Okay.
All right, so that's why zeros are added to the front to make it another 8 bits long. So latter part will be stored in the latter byte, and first part will be in the first byte. Okay, so let's now think about, so let's think about this 2 byte memory. So if I allocate 2 byte of memory for my number, Then this number 1279 has these ones and zeros shown in this picture. Now, do you agree with me that if I replace one of these zeros with 1, then the number is larger, right? That adds another power of 2, right?
Yeah.
2 to the power of
Yes.
something.
Yeah.
Yes. Yes.
Yeah, we don't care what it is. It adds 2 to the power of something.
Correct.
If I replace this 0 with 1, that'll make it larger. So
Yes.
if these zeros are replaced with 1s, the number will get bigger and bigger. So can you tell me what is the binary code of the largest number that fits in 2 bytes? What would be the binary code?
One's, wait, 1 1 1 1. Oh, like the whole lot.
Right. The number that has 1 1 1 everywhere, right? 16 ones in the binary code. The number that has 16 ones in the binary code is the largest number that fits in 2 bytes of memory. Okay, so the largest number that fits in 1 byte of memory is the number that has 8 ones, right?
Okay.
Okay. So let's convert this number that fits in 1 byte of memory into decimal number. We already learned how to do that. The last one represents 2 to the 0, 1 times 2 to the 0, and the previous one represents 1 times 2 to the 1, and so on. All of them have 1 times 2 to the power. So what is the power for this first byte, first bit, 1? 2 to the power?
2 to the power of 8.
2 to the power what again?
7.
7.
Yeah, it goes all the way to 2 to the power of 7.
Right, 7. There are 8 bits here, so because we are starting at 2 to the 0, it'll end up at 2 to the 7, right?
Correct.
Okay. So if I simplify this, find value of 2 to the 7, 2 to the 6, all those, add them up, I will get 2 to the 255.
250. Yes. Mhm.
255, okay? It's a long calculation if you do it
Yes.
manually, but it's 255. So 255 is the largest decimal number that can be stored in 1 byte of memory. Okay, 255. Now these facts are useful to remember because there will be questions coming up in the homework and test as to what is the largest number that fits in 1 byte, 2 byte, 3 bytes. All those will be your questions in homework and test. So you have to be able to figure it out. This 255, this calculation is kind of long, right? To calculate all this, this series, this sum of these series in the calculator. So we have a formula that will be useful. 2 to the 0 plus 2 to the 1 plus 2 to the 2 all the way to 2 to the power n is equal to, now this is something, you may have learned in your math class in your high school. Some of you may have, some of you may not have. It's called a geometric series. So we can write down the sum of these as a formula. 2 to the power n minus 1. So I'm sorry, 2 to the power, yeah, if it ends at 2 to the n, then the value will be 2 to the power n plus 1 minus 1. Subtract 1 from that. Let me show you this series we just calculated. 2 to the 0 plus 2 to the 1 all the way to 2 to the 7, right? That would be equal to, if it ends at 2 to the 7, then 2 to the n plus 1 is 2 to the 8, right? Understand what I mean? Let me,
Yes. Yes.
yeah, but let me, so 2 to the 8 minus 1, that's the value. So let me start over. Clear the screen. Okay, so formula is 2 to the 0 plus 2 to the 1 all the way to 2 to the n will be equal to 2 to the power 2 to the power n plus 1 minus 1. That's the formula you need to memorize. You're going to need to memorize this. If you didn't learn before, just memorize it. Now, I don't memorize, I can quickly calculate the formula in my head. But, you know, you'll have to, this is the only formula you need to memorize in this chapter. So 2 to the 0, so 1 byte of memory, the largest number that fits in 1 byte of memory has a decimal equivalent number, which is equal to this, all the way to 2 to the 7. And that will be equal to, according to the formula, 2 to the power 8 minus 1. 2 to the power 8, you can calculate in your calculator. By the way, you need a calculator that can compute exponents. For your homework and for your test, you know, you need a calculator. So 2 to the power 8 can be computed in the calculator. That will be 256. Subtract 1, you get 255. And that's your largest number that fits in 1 byte. So you have to be able to calculate these things. So right, I have shown that here in 1 byte. The largest number that fits in 1 byte is 255. Now I'm going to just show you something about 2 bytes, but the largest number that fits in 2 byte is a homework question, but I'm going to just give you the ideas. These ones in the second byte will be the letter part of the code, ASCII code. The ones in the front are the front part of the ASCII code. They're all going to be 1 for the largest number that fits in here. So this corresponds to 2 to the 0. The next one corresponds to 2 to the 1. So this goes from 2 to the 0, 2 to the 1, all the way to 2 to the power what?
7.
That will be in 1 byte, 2 to the 7.
Yeah.
We're talking about 2 bytes here.
To the 15th?
15, right. So the largest power is 2 to the 15 for this number. I'll leave it at that, and you figure out the rest for the homework. The formula is also given here in this page, and it's there in your book. You know, the book it tells you everything a little bit more detailed. You know, whatever I'm saying will have to be written in the book. So that's why this presentation doesn't have all the words in there. But you get the point. This formula in the box here that you need to remember, because your question in the homework and test can be dealing with different number of bytes. You know, I can ask you what is the largest number that fits in 3 bytes of memory or 4 bytes of memory, all those questions. So you have to be ready for any of those. Okay, so here is the what is the largest number that can be stored in 2 bytes? What is the largest number that can be stored in 4 bytes? So let's go over this one, 4 bytes of memory. The 2 bytes is part of homework. I'll let you do that at homework. So let's do the 4 byte. Okay, so here is 4 byte. So the ones in the last bit would correspond to 2 to the 0 plus 2 to the 1. And so altogether, there are how many bits are there when you use 4 bytes? 4 bytes equal to how many bits?
35.
32, right?
32.
31,
32.
32.
32.
32 bits are there. But if I write these powers, 2 to the 0, 2 to the 1, 2 to the 2, where do I end?
2 to the 31.
31.
No, 31.
Yeah.
There are 32 bits, but since the powers start at 0, the highest power will be 31. Okay, now apply the formula and tell me what is the value of this, the value of the sum of all this. So apply the formula. That's what I, so it's equal to what? 2 to the power of what?
2 to the power of 32 minus 1.
Right. 2 to the power of 32 minus 1. If the powers end at 31, then the sum of those will be equal to 2 to the 32. One more. Minus 1. And 2 to the 32 can be calculated in your calculator, right? Now this is in your book, this value of this number is wrong. And that's one of the reasons I'm doing it right now. Hold on one second. But remember I said there are corrections of the errors posted on your Blackboard. There, that number is corrected. And so that's why you need to make those corrections in your copy of the book. I'm going to do it on the calculator right now. So let's go to the okay. On the calculator, I'm calculating 2 to the 32. So clear memory. 2 power 32. Okay, and then you subtract 1. So I have 4,294,967,296. So if I take 1 off, 295, the last digit changes. Okay, so this is the largest number that fits in 4 bytes of memory, 4 billion. So in C++ language, standard memory allocation is 4 byte for a number. So if you declare a variable, if we declare a memory cell as one that will hold a number, then it will allocate 4 bytes of memory for it. So therefore, the largest number that will fit there will be this 4 billion, 4 billion. You are going to be, you're going to have to be able to calculate the largest number that fits in any size memory. So I think we have had enough practice and you should be able to do that. So the other coding systems are our next topic. The binary coding, we went over the decimal coding, which is what we normally use. And we understood the details of, why decimal coding and what the details, how exactly the numbers are coded in the decimal code and all that. And then we went over the binary coding system. The reason for binary coding system is because the computer can only handle 0 and 1, two different things. And therefore, only binary coding system has 2 symbols to represent all the numbers. Now, can we use other base instead of 10 and 2? Can we use other bases? Basically any base can be used, but why? We don't normally have any reason. But after the computers were invented, the code, the base of 8 and base of 16 have become important. And therefore, right now in this course, we will not be using the coding with the base 8 and 16. But when you go into more advanced computer science, you'll be using them. And that's why I'm supposed to teach you these coding systems now. So I'm going to have to go over the coding system with the base 8 and the coding system with the base 16. When you use base 8, it's called octal coding system. Octal coding system means 8 will be the base, so that means we have to express the number as sum of powers of 8 to find the code. So I have written this here, but I'll explain how to find it on the board. I'll explain how to find the octal code using this method. You have to express the number as sum of powers of 8. So where do we begin? So let's write 459 equal to, start at a to the 0, go up a to the 1, a to the 2. A to the 2 is 64, and a to the 3 is too big. So therefore, a to the 2 is the largest that can fit in here. And once you write that, you have to now figure out what number will go in front of it. Now, like I said before, if the base is 8, all the numbers that will go in front of it will have to be less than 8, right? There's no reason to write an 8 here because 8 times a to the 2 is a to the 3. That would have been separately written as a to the 3 if there is an a to the 3 in this number. And there is no a to the 3. So therefore, we never have a reason to write 8 anywhere. It'll be only less than 8. So less than 8 means 0 through 7 can go in front of it. So I need to figure out what number will go in front of a to the 2. Now, in the case of binary code, it's always 1 for the largest power. It's always 1. But here, the number in front of a to the 2 can be anything less than 8. I had to figure it out. So 68, a to the 2 is equal to 64. So I need to decide what number will go in front of it. I have to just divide 459 by 64 to see how many 64s are there. And it came up 7. You can use calculator. Divide 459 by 64 in the calculator, you'll get 7 point something. That means 7 whole number, the fractional part will have to be discarded. So the 64 goes into 459 7 times. That's all we need. So therefore 7 goes in front of it. Now, to find the rest of it, you have to find 7 times 64. So 64 times 7, you have to calculate that. That's 448. So take away 448 from 459. That gives you 11. Okay, so that means we can have 1 a to the 1. We have 11 left. So therefore, you put 1 in front of this because 1 a to the 1 can be included. This is equal to 448. And this is equal to 8. So 456. And there are 3 left after that. So you put 3 in front of a to the 0. A to the 0 is 1. So therefore, this add up to, this expression now adds up to 459. So these digits in front of the powers of 8, 7, 1, and 3 will be the code. 713 is the octal code of 459. So go ahead. Question?
No, I got it.
All right. So that's the binary, the octal code of, this is the octal code of 459. We read it as 713 because it's not 700. The 7 doesn't represent 100, right? So these are now, the 7 represents 8 of the 2s. So you read it as 713. Anyway, that is your octal code. Now, can we use the shortcut method? Yes. So let me show you that. 459, to find the octal code of 459, you have to divide by 8. So 8 is the base now. Divide by 8 repeatedly. 8 goes into 459 7 times, but 7 times 8 is 448. So therefore, 11 remainder. No, 8, 7. Eight goes into 459 7 times. And yeah, so 7 times 8. 7 times, I'm sorry, I'm mixing up here. Let's redo it. 8 goes into 45 5 times. And then there's a remainder of 5, so 59. 7 times, yeah, 57. So 8 goes into 459 57 times with the remainder of 3. So now divide by 8 again. 7. 8 times 7 is 56. So there's a 1 remainder. That's it. Then the number is now less than 8. So until you get the number less than 8, you have to keep it going. So 8 goes into 459 57 times. You can use calculator for this. You just divide 459 by 8, 57 point something will be the answer. You just disregard the decimal part, write the 57, the whole number part. Now divide the 57 by 8. So 8 times 7 is 56. So therefore, yeah, therefore 1 remainder. So now reading from bottom up, 713 is your code. So the shortcut method can be used for octal coding also. Here's the shortcut. Yeah, shortcut method right there. The next one is hexadecimal code. But we are now out of time, so I'm going to stop here. We will proceed from hexadecimal code in the next class. So today, your homework assignment says it's problem 1 through 14, but 16 is added to it. So the link on the, remember the link I set up on the Turnitin assignment setup? That link will tell you exactly which problems are due in that assignment. So I'll make sure to add the 16. So problem number 16 has been just added to your homework. All right. So it's going to be even numbered problems from 1 through 16. All right.
Professor.
Yeah.
So you want us to put it on like either Word, right?
Yeah. Any editor will do.
Okay.
Yeah. So Microsoft, the Windows come with 2 editors. One is Nodes, and there's another one. What is that? I forgot the name of it.
Notepad.
Notepad. Yeah, Notepad, right. So the Notepad is a simple editor, like word processor, but it doesn't have the fancy features of the word processor. That Notepad will do. If you don't have a word processor, just use the Notepad. But typing is necessary because otherwise, like I said, otherwise things don't work very well. My feedback would not work very well. So, it doesn't take much time. Just type things. You never have to type the question, just type the answer. So if your answer for a question is, here is a binary number, what is the decimal equivalent? If the decimal equivalent is 56, you only write 56, that's it, right? So don't write anything unnecessary. You're not showing work, you don't have to, but you can do the work somewhere else, but present the answers on a paper and submit that. All your work will be expected to be your own. If you cheat in the assignment, you're cheating yourself. You won't be learning enough to pass the course. I have seen students cheating in the assignment. They only ended up failing the course. Can you cheat in the test also? Very difficult, but I have found students cheating, and especially in the online testing, now we had to do online testing, right? So last semester, I have found 6 students cheated in the test. What did they do? Failed all 6 of them. They thought I wouldn't know, right? I figured out that they cheated. And I also reported that to the vice presidents, and they are under investigation now by the vice president. So they might punish them further. But you fail the course. If anybody cheats in the exam, fails the course. So please do not try to duplicate anybody else's work. No use. You have to do these yourself. Like math, these only you can learn by doing it. If you don't do it and have copy somebody else's work, you will never be able to pass the course. Okay, so please do the work yourself and only present your answer and submit that to the Turnitin assignment. So let me remind you, I have office hours at 2 o'clock. If you have any question, you may want to try these problems before that office hour time so that you can have a chance to ask questions. Also, the tutor will be available at 4 o'clock Thursday. Yeah, that's tomorrow. Feel free to bring up your questions in those meetings. All right, enjoy the rest of the day. I will see you Monday. Have a nice weekend, everybody.
One more thing, Professor. When we uploading the assignment, you want it in doc file, right? In Word file, not PDF file.
It can be any format. PDF
Okay.
so accepted, but there's no
Okay.
way to convert to PDF. You can upload doc, docx, anything.
Mhm. Okay, so it doesn't matter. You don't prefer which one, right?
No, because I will not be editing. I will be only.
Okay,
I will not.
I see.
Yeah, I'll be only putting my feedback. The feedback can go on any document.
Gotcha.
No matter
All
what
right.
format it is, even if it is
All right.
JPG. Okay.
Okay, sounds good. All right. Thank
Professor,
you.
I was having connection problems, but I was here for the entire course, but I was just coming in and out. Did that affect my attendance?
No,
No, it didn't.
no, it doesn't.
Kept connecting
The
in.
technology has its own problems, so we all understand that.
All right, thank you. Just want to make sure I was here.
All right. Yeah, I got you.
Thank you.
When are our assignments due? When are our assignments due? Sorry about that.
Always due in the 10 minutes before 5 minutes before the next class.
Okay, thank you.
Bye, everybody.
Take care, Professor.
Thank you, sir.
You too.
Bye, Professor.